Last time, after the syllabus, I explained one topic. Yeah, so let's start from there. In that one, 8.1, we understand the algorithms from one angle. So what that angle? That is from the problem solver's angle. Yeah. We are problem solvers. So from that angle, problem solver's angle. So today, let's look at our 8.2 from another angle. So what's that angle? Yeah, it's the, computer programmer's angle. All right, yeah, from this angle, yeah. So let's look at that, yeah. First, our goal this time, find a solution for a computing problem. The solution, we need to write a computer program. That is our solution, all right? Coding, that's the solution, all right? To find a solution, yeah, this time we need a precisely defined procedure to solve the problem, okay? Yeah. So here we emphasize the details in our problem-solving procedure. Yeah. And in this procedure, we need to provide step-by-step implementation details. Okay. Yeah. So here I use this picture. Yeah. That's just an example of the flow chart, right? In order to organize your thinking, you may like to draw a flow chart. Yeah, usually for a relatively hard problem. Yeah, so you need to really do a lot of planning. Yeah. All right. Okay. Yeah, a lot of planning. Yeah. Yeah. Here, this flow chart way. All right. Yeah, pretty common. Next. Oh, some problem. Yeah. Each step can be presented in code. Yeah. So here it means when you draw that flow chart, you need to make sure each box you can use coding implementation to make it happen. Otherwise, it is useless, right? Yeah. So we understand that. Then it results in a computer program. The end product is a computer program. Yeah. So we understand that part well. All right. So then from that angle, what is an algorithm? Yeah. From that angle, we want to understand our algorithm. That is a sequence of instructions. Yeah. Computer instructions. All right. So unambiguous. Yeah. It must be very clear. Oh, just to finish last few lines here. All right. Yeah. Then we start a new topic. All right. So instructions must be unambiguous. Then input must be legitimate. Okay. So we call a data validation step. We must make sure the input is valid. Yeah. And the output must follow some required format. So that format is determined by our users, our customers. So here we assume we provide business solutions to our customers. Okay, so the customers, they tell us what kind of output they want. All right, so we need to really make our customers happy. Yeah. So acceptable. Yeah. Then the executable time based on our textbook, it says finite amount, but that's the minimum, right? Finite amount, because there is a big difference on the response time or execution time. So I want to write it as acceptable to our users. If the users feel our solution is too slow, then it's not acceptable, right? We need to improve the solution. Otherwise, we won't get paid, right? So we need to make our users happy. All right. Okay, so that's the topic 8.2. Yeah. So we finished that. Now I want to start a new topic. Yeah. I hope when I start a new topic, there is no interruption, so I can run from beginning to end. All right. Before I start new topic, any question? Yeah, any? So you can, because in the presentation in the middle, I may like to run from beginning to end. Yeah. First, let me switch to the new PowerPoint slides, part B. Yeah. I haven't posted. After the class, I will post it. Yeah. All right. Part B, the topic is efficient polynomial evaluation. Yes. Yeah. I use several subtopics to present this big topic. Yeah. B.1, evaluate the polynomial. Yeah. So let us look at our problem first. So that is our problem number 1 for this class. Now, I will follow the natural order 1, 2, 3, 4, 5. Yeah. A sequence of computing problems we will solve in this class. The first one in that sequence, evaluate a polynomial. Yeah. Yeah. Given a polynomial, yeah, you know the polynomial, right? The format of the polynomial. Yeah. With coefficients a0, a1 through an, the given coefficients are provided as an array of real numbers. Yeah. Then we will have value of variable x. Yeah. Every time we will have a different x value. Yeah. Then the question is how to evaluate p of x efficiently. Yeah. Here I emphasize efficiently. I need to change the pen color. Yeah. Okay. All right. Yeah. So here I emphasize efficiently. Yes. Because why here I emphasize the efficiency here? Because if you calculate the value is, very slow, it's not acceptable. Yeah. In the previous topic, I said, if our customers are not happy about our solution, then it's a failure, right? So efficiency is extremely important here. Yeah. Then you also see here, I give you the reference of this topic, section 6.5 on our textbook. Yeah. So you can see in our first module, we jump to that section 6.5. So why is that? Yeah. The reason is because I want to start our project, programming project number 1 quickly. Project 1. Yeah. This is the topic. Evaluate a polynomial efficiently. That is the topic for our project number 1. Yeah. So after this topic, we can start our programming project 1 as early as possible. Okay. So that's the reason. Definitely, there is another reason I want to use this computing problem to show you the power of algorithms. Yeah. Another purpose to have this material earlier, show the power of algorithm. right? Yeah. How powerful it is. Yeah. Power of the algorithms. Yeah. Give you some strong impression. Yeah. All right. So let's start. Yeah. All right. Let us do first try, because everyone, I believe everyone here in our class knows how to evaluate a polynomial, right? Yeah. So I think you can write a program immediately to calculate the value of a polynomial. Yeah. So our first try, let us just use the method that everybody knows. Yeah. We call it straightforward algorithm. All right. Yes. Because this straightforward algorithm, there is another name, call it brute force method. Brute force method. Yeah. Later, in our module 3, we will study brute force method another time. Yeah. Here, just the first time, we use the brute force method. All right. How to do it? Work on each term. Yeah. This polynomial, there are many terms, right? Look at how many terms do we have here in the polynomial, right? How many terms? We have n plus 1 terms, right? Total, we have n plus 1 terms. Now, we just take one of the n plus 1 terms as the representative here. This one is the representative. A sub k times x to the kth power. Yeah. This is the representative term. Yeah. Now, can we count how many multiplications do we need to calculate this term? Right? Can we do the calculation here? All right. Yeah. So to find the number of multiplications here, yeah, here, yeah, just a minute. Yeah, just a minute. Let me, yeah, because I may like to, yeah, yeah, I like to view the chat message area. Yeah. All right. Yeah. Here I can see it. All right. So when anyone can type the answer, how many multiplications do we need to find this term, to find the value of this term? Anyone? Yeah. The answer is short. To calculate. Good. Yeah, good. I saw. All right. K or N. Yeah. Yeah, but I know your meaning. Yeah. Let's use K. Yes. So here, let me summarize. There are two answers here. One is K. The other is K plus 1. Right? Yeah. So based on the response. All right. One must be correct. Oh, sorry. One of the two must be wrong. Right? Yeah. We cannot say one of the two is correct, but we can say one of the two must be wrong. Yeah. But how do we determine that? Right? It's a simple question, but I like to introduce a simple, effective strategy. So here, let me give you the strategy. In our first class, I talked about strategy. From now on, we need to apply effective strategies to solve our computing problem. Here, our first strategy. Okay, yeah. Try simple cases. Yeah. Here, we need to determine which of the two answers is incorrect. Yeah. So here, we try simple cases. Yeah. When k equals 1, so we have a1 times x. How many multiplications do we need in this simple case? The answer is 1 multiplication, right? When k equals 1, we need one multiplication. Let's try when k equals 2, the term becomes a sub 2 x squared. How many multiplications do we need? A2 times a squared, right? 2 multiplications. Answer is 2. Can you see the relationship? Our answer and the k values, when you compare, they are the same, right? Our answer is the same as the k number. So you can see from the 2 options we have so far, so we can say k should be correct, right? K plus 1 incorrect. All right, yeah. So you can see this is the, our result from our first strategy. Try simple cases. Yeah. So the answer is K. Okay. All right. Now from there, the question is your algorithm efficient? Yeah. Here we have the answer. Each term we need k multiplications. Then we combine n plus 1 terms. We have the total number. Yeah. But here the question is, if we calculate the polynomial value in this way, do you think your algorithm is efficient? Yes. How do you know it is efficient? Right? Because this question is subjective, right? Subjective. It is not objective, right? Not objective. Because in different people's minds, the efficiency of the algorithms will be different, right? Some people feel, think about this. If some algorithm give you answer in 5 seconds, for some people, they may feel it's okay, I can take it in 5 seconds. But for some people, they will say it's too slow. I cannot accept it. 5 seconds, too slow, right? So that's why I say it's subjective. Yeah. We may like to have an objective answer for the efficiency. Yeah. So we need some objective way, objective way to describe the algorithm efficiency. Yeah. So here I put this some performance number. If we can use some concrete number to describe algorithm efficiency, then we can say it's objective, right? Because for different people, if we use the same number to describe the algorithm efficiency, that's the same. Everybody uses the same number to describe one particular algorithm. So that's the objective measure. Yeah. So we call that. So we like to have objective measure, algorithm efficiency measure. Okay. Yeah. All right. But this question, the measure question, we will answer later. Yeah. Later, we will spend a lot of time to answer this objective measure question. All right. Yeah. Let's move to the next one. Are we satisfied with this solution? Yeah. Another important question, right? Are we satisfied with this solution? Yeah. Yeah. But here, we only have one solution, right? We only have one solution. No matter you're satisfied or not, if I ask you to solve this problem, you have to take the same solution, right? You have no other options. That's the only way you can take, right? Yeah. So to answer this question, if we are satisfied with the solution or not, we would like to explore other options. Yeah, so we like to explore other options. And if we have other options and we can do comparisons, after that, then we can say if we are satisfied with the solution or not. Okay, yeah. So at this point, we do not know it. Yeah, we do not know if our algorithm is good or bad. Yeah, because no comparison. Okay, we do not know how bad it is. Okay, all right. So let's move to the next step. Yeah, we like to some analysis on this, algorithm efficiency. We try to get more information. Yeah. All right. The first question, do we need an algorithm here? Because this problem is so easy, right? Everybody knows how to do multiplications, how to do additions. Why we need some fancy algorithm, right? Yeah, it sounds like nobody needs an algorithm in solving this problem, right? Yes. So let's try to go a little further. Yeah. Although it only it contains addition and multiplication, but the question is, do we have different ways to do additions and multiplications? All right, yeah, so here, from this observation, so question, do we have different ways to do those additions and multiplications? Right? Yeah. Multiplications. Yeah. So that question we need to answer. Yeah. Later. Yeah. Not at this time. At this time, we do not know if we have different ways to do these additions, multiplications. Yeah. We only know one way to do it. Yeah. But we need to explore much more. Yeah. Yeah. Until after we collect a lot of information, then we are ready to find different ways. Yeah. Here, next question. Can we use execution time for what? Execution time to measure the algorithm efficiency. Yeah, that's the question. To measure algorithm efficiency, because execution time is straightforward, right? Yeah, everybody, when you see that execution time in number of seconds or in number of milliseconds or in number of microseconds or nanoseconds, yeah, you have an idea how fast it is, right? Yeah, so it is a legitimate question. Can we use the execution time to measure the algorithm efficiency? Because we can call it objective, right? This is some objective measure, right? Yes, yeah. So here, actually, the answer is no. No is the answer. Why? Let me point out a little more detail here. Yeah. First, let's look at from the hardware side. When you calculate when you measure the execution time, yeah, think about if you run your algorithm on a supercomputer, all right, yeah, supercomputer. All right, it is very fast, right? You can get an execution time number. Then you try some low-end computer, okay? Some cheap low-end computer. Then the execution time must be different, right? Can you compare them? Both execution times for the same algorithm. So definitely if you use execution time, you cannot describe a particular efficiency of a particular algorithm in a fair way, right? Yeah, it's not a fair way, okay? Yeah, if you use supercomputer, you have an advantage over that low-end computer. It's not a fair way, right? Yeah, that's the hardware side. How about software side? The software side, coding. Yeah, here, let's just, talk about coding side. Yeah. When we implement the same algorithm in our computer programs, different programmers can write different type of code, right? Yeah, different programmers. Some super, some senior, some smart programmers can write much more efficient programs than some beginner programmers, right? Yeah. So if you compare, although we use the same machine, yeah, so we can make two programmers using the same machine, but their programmers are different. Then the result could be different, right? The execution time could be different. Yeah. So that means both from hardware side, software side, that execution time as a measure, it's not a good measure. It's not a, let's say, it's not a stable measure. Not a stable measure, right? Yeah. So we want to avoid that. We want to avoid that kind of issue related to hardware and software. Now you can see in your mind, in order to get a fair measure or stable measure, we want some measure that does not rely on hardware, software, it has some very stable number. That's our goal, okay? Yeah, so our goal here, get a stable measure for algorithm efficiency. Yeah. All right. Okay. Yeah. It's a long journey. Yeah. So yeah, what's that? Yeah. So, yeah, I just using, right. So the answer, yes, sorry, I have to erase. Yeah. Next time I try to find a better way. So I do not erase my handwriting. Yeah. Yeah. I try to improve. Okay. I try to improve. So this is the answer. So what is a stable measure? Yeah. Using number of additions, number of multiplications to measure algorithm efficiency. Okay. Think about that. Yeah. If we just use the number of additions, number of multiplications together, can you see the measure is quite stable here, right? It does not rely on your hardware, right? No matter you use supercomputer or low-end computer, you have same number of additions, same number of multiplications, right? Yeah. If you are an experienced programmer, you can write a super efficient program comparing with another beginner programmer. The program is not quite efficient, but you both should use the same number of additions and multiplications, right? Yeah, for the same algorithm. What I mean, for the same algorithm. Yeah. So that means this measure, this measure way is stable. It is objective and stable. All right, yeah, here. So we just get that point. Yeah, let's go to next one. Next one, we need to calculate. We need to use the number of additions and the number of multiplications to measure the efficiency of our straightforward algorithm. Yes, yeah. But here there is one comparison problem. Yeah, here I want to point out another comparison problem. What's that comparison problem? Yeah, in our real life, can you compare an apple with a pear? Right? People always talk about that. Yeah, you compare an apple with a pear. That's a not good comparison, right? Yeah. Here we have that situation also. We have addition and multiplications. They are different operations. Yeah. If we need to compare addition and multiplication, can we have a fair way to compare? Right? So that's why I say we need to fix that comparison problem. Do comparisons between additions and multiplications. Yeah. Here we need to do that. Yeah. We cannot avoid that, right? Yeah. Because finally we have to tell our users the algorithm efficiency measure is certain number. Yeah, we have to, not our users, probably ourselves, right? Because our users may not care about that number, right? Yeah, yeah. Ourselves, we care about that number. Yeah. All right. So here we need to add some reasonable assumptions. Yeah. Here I make assumption like this. Each addition takes 1 unit of time. Yeah. That time period may not be fixed. Okay. Now, here we just make it 1 unit of time. Yeah. Then for multiplication, each multiplication takes 10 units of time. Okay. We make this assumption. Yeah. So here you can see multiplication is much slower than addition. Yeah, we have that experience, right? Multiplication in computer is much slower than than addition in a computer. Yeah, and it is approximately 10-to-1 ratio. Yeah, so although not exact 10-to-1, approximately 10-to-1. Yeah, so here let us just use this kind of assumption in our analysis discussion. Yeah. Because in that way, we can avoid comparing apple to pear, that kind of situation. Okay, yeah. All right, yeah, yeah. All right, so let me go back a little bit. Yeah, regarding the comparing apple with a pear, here, after our conversion, our apple, yeah, we convert our addition to 1 unit of time, and we convert 1 multiplication to 10 units of time. Then, when we look at the total number of time units, then we can unify additions and multiplications under the time units umbrella, right? Yes, that's our goal. That is the reason we take this reasonable assumptions. Yeah. All right. Yeah. Any question, just let me know. Okay. All right. Yeah, let me continue. Yeah. Now our goal becomes finding the number of time units. Yeah. All right. Addition, 1 time unit, multiplication, 10 time units. Yeah. Here, let me give you a little more information about the time unit here. Yeah. For our modern computers, here, when we talk about our modern computers. Yeah, yeah. Because, yeah, modern computers, then to do one addition, we just need small number of nanoseconds. Small number of nanoseconds. Yeah. Yeah. And multiplication, then approximately 10 times of that. Yeah. So we use that as the time unit. Yeah. Nanosecond. Do you have idea on the nanosecond? Yeah. Just remind you, yeah, 10 to the negative 9 second. Yeah. 1 nanosecond. 1 ns equals that number. Yeah. 1 billionth of second. Okay. Yeah. 1 billionth of a second. Yeah. All right. Yeah. That's the one. Yeah. I have that. Yeah. But the nanosecond, sometimes people also use the notation Greek letter mu s. Okay. Mu s. Yeah. Another notation for nanosecond. Yeah. Yeah. All right. Now our analysis. Yeah. It is allowed to add reasonable assumptions. Yeah. We do some reasonable assumptions. Yeah. All right. Yeah. The added assumptions should not alter the original problem significantly. Yeah. If our assumptions make our problem significantly easier or harder, then it's not a good assumption. Yeah. We should not take that kind of assumption. All right. Yeah. But with the current assumptions, you can see the problem is the same, right? Yeah, the difficulty of the problem is almost the same. Yeah. So we do not alter it. Okay. Yeah. But the advantage of that assumption, it simplifies the setting without changing the difficulty. That's the reason. Yeah, we take that assumptions. All right. Now, the next topic, estimate the cost. Now we can do the work. Yeah. The previous discussion we just completed, that's the preparation. Now, the real work we need to do, estimate the cost. Okay. Yeah. So here, the subproblem number 1, count the number of additions. Now let us count the number of additions we need. Do counting. Yeah. Yeah. I call it subproblem number 1, but we have subproblem number 2. Count the number of multiplications. Yeah. Let us do one by one. And this one, it's an easier one. Yeah. Yeah. So let's do it. Yeah. Can you see n units of time? Yeah. N units or n plus 1. Yeah. Here, 2 possible answers. N units of time or n plus 1 units of time. Can you see that? Similar to our previous question, k multiplication or k plus 1 multiplication, right? Yes. Because here we have n plus 1 terms. Yeah. So you need to really figure out if we need n units of time or n plus 1 units of time. Okay. Yeah. How to find it out? Can you still use our old our previous strategy we used before? Our old strategy, try some simple cases. When n equals 1, how many additions? N equals 1, you have n0 plus a1x1, one addition, right? When n equals 2, you have a0 plus a1x plus a2x squared. How many additions? 2, right? So the same number as the n for the number of additions. Yeah, so that's, we get this n units of time. Yeah. All right. Here, I also want to introduce a counting technique here. Yeah. Other than we try some simple examples, I also want to introduce another effective method, counting technique. Yeah, here I call it counting by reference. Yeah, so this idea matches our real life experience. In your real life, when you need to make appointment with your friends, many times you need to, for example, you need to meet in some specific location, you need to find some reference, right? Yeah, some building as the reference or some street as the reference, right? Yeah, here in our math problem solving, we also need to use some reference. Yeah, here, let me point out the reference we need. Yeah, all right, so here, yeah, let's take a look. One addition corresponds to one plus sign, right? When you see one plus sign, you do one addition, right? When you see two plus signs, you do two additions, and so on, right? Yeah, so here we observe this property. Yeah, but the question is here, if we want to count the number of additions, we need to count the number of plus signs. The question is how to keep track of those plus signs. How to keep track of those plus signs. We get lost, right? Here, if you, because look at the dot, 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 many dots, the dots, we skip many terms. When you see those dot, 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 we get lost. We couldn't keep track of the number of plus signs, right? So you need a smart way to make you keep track of the plus signs, right? Yeah. So here, let me use that so-called counting by reference. If we can choose appropriate reference, then we can keep track of the plus signs. Yeah. Look at this. The subscript 1. All right. The first plus sign, I make it corresponds to the first subscript of the coefficient A1. The second plus sign corresponds to the second subscript A2, and so on. The last plus sign corresponds to the last subscript A sub n. In that way, we can keep track of the subscripts, right? Yeah, it's very easy to keep track of those subscripts. How about that? Okay, the subscripts 1, 2, 3 through n. how many subscripts do we have here? Right? And subscripts. And subscripts. All right? Yeah. That's the so-called counting by reference. How about this method? Okay. Simple and effective. Yeah. All right. Now let me summarize this method. The essence of this method. All right. We discover one-to-one correspondence between two mathematical objects. Yeah. Here, the first mathematical object is addition. Yeah. Yeah. The first object, addition. The second mathematical object is subscript. And we find one-to-one correspondence between these two mathematical objects. Yeah. Then, if we have that kind of relationship, then we can do the counting easily. Yeah. Here I use a small diagram to explain this method. Yeah. We have object 1 and object 2. Yeah. There is a one-to-one correspondence between them. Yeah. Make sure one-to-one correspondence. Yeah. Now we need to do the counting on object 1, but it is hard to keep track of. Yeah. Due to some reason, it is very hard to keep track of the number of object 1. Yeah. But it is very easy to keep track of the number of object 2. Yeah. Object 1 hard to count, but object 2 easier to count. Then we just count the number of object 2, and we can get the number of object 1 from number of object 2. That is the essence of this method. Yeah. All right. So with that, this is the first time we use this counting method. Yeah. The answer is N. Yeah. Next time we will use another time. Yeah. I hope you can, get used to this thinking. Yeah. So we need this kind of thinking. Yeah. All right. Any questions so far? Yeah. All right. It is near the end of the class. Yeah. Today we do not go very far. Yeah. Yeah. Because at the beginning, so we need to set up environment. Yeah. So that's why I couldn't complete all the materials I plan to cover today. Yeah. All right. So I think I just, let me see. Yeah. Let me leave the next slide next time. Yes. Yeah. So let me just stop at the previous slide. Yeah. Yeah. All right. Yeah. Because we I have a lot of material for the remaining of this part B. Yeah. So next time, I think I need about 30 minutes to complete the remaining material. Yeah. All right. So that's it for today. So if you have any questions, you can ask me. If you have no question, let us just, leave the meeting. All right. Yeah. And we will see next week.